Hello, this is great. This is your science video for Friday, February 19th, and we are excited to have that week over, I'm sure. Today we are doing pages 218 to 221 in our reading, but then we're also doing the properties of sound definitions, and then also the study guide, which is 147 and 148, that goes through basically the things that you have learned. Now, focus on a couple of things. Number one, the picture at the bottom there with the spring, you will see again in a test. And so you want to make sure that you know that pretty well. And then also, and you may see it in a quiz as well. And then also on the back of page 148, on the bottom there, it has two word problems in a sense. I mean, it's describing some things. And you need to answer the question as to whether what that answer is. That you may also see one of those on a test as well. So just wanted to be aware of that. And let's go ahead and get our books out, and we're going to be reading starting on page 218. And so here, talking about properties of sound waves. Engineers like Mr. Fogel must understand sound to design technology that can be used to help others. What do you know about sound? Sit quietly for a moment and listen. And so if you do that, you may hear some things. And so I'm going to do that right now, and you do the same thing. So one of the things I can hear is I can hear a vacuum going on, or that's running over in Mrs. Smith's room. I can hear the click of the clock behind me. I hear children, Mrs. Smith's children over there, talking to each other. So there are little things that you can listen to. Sometimes you hear vehicles go by. Sometimes we hear sirens as ambulances or fire trucks go by, or police cars. And so it says you may hear the hum of air moving through a vent, or the ticking of a clock. Perhaps a noisy truck or train is passing nearby. A chair may squeak, or shoes may rustle on the floor. Although each sound is different, all sounds are made in a similar way. Each sound started because an object moved. Vibrations and waves. The movement of an object causes vibrations. A vibration is a rapid back and forth movement. Sound is a vibration that can be heard. The ticking that comes from a clock is caused by the movement of the parts inside the clock. The parts vibrate as they touch each other. They cause the air molecules around them to vibrate too. These vibrations blend together to make the ticking sound that you hear. Sound moves through matter in waves. A wave is a disturbance that moves energy from place to place. Look at the fantastic fact there. You may have heard the shrill trumpet sound that an elephant makes, but the deep growling or rumbling noise is a more common way that one elephant communicates with another. Infrasound is a sound below the level of human hearing. Many of an elephant's rumblings use infrasound. The vibrations of an elephant's infrasonic messages and warnings can be heard by family members miles away. Both humans and elephants make sounds as air causes their vocal folds to vibrate. Vocal folds are strips of tissue that lie across their airways. An elephant's rumbling sounds are made as puffs of air cause its vocal folds to vibrate. The vocal folds of an elephant are about 8 times larger than those of a human. Its very large folds vibrate much the way a flag flaps in the wind, resulting in the low infrasound. All right, so back to page 219 now, and you see the parts of the sound wave, the compression and refraction. The matter through which a sound wave travels may be a solid, liquid, or gas. Most of the sounds that we hear travel through the air. Sound energy moves from the vibrating object to the ear. You hear sounds because the vibrations of sound energy cause your eardrum to vibrate. As the vibrations are carried through the bones of your middle ear, the vibrations are changed into nerve messages. Your brain then interprets these messages and tells you what you hear. Sound waves can be described as mechanical waves. Mechanical waves must have matter to travel through. Energy, so that makes you understand the difference between these different waves. Mechanical waves must have matter to travel through. Energy causes particles in the matter to move and vibrate. Sometimes you can feel sound waves. When you hum, you can feel the vibrations that your throat makes. Those vibrations cause the sound that you might hear. Other sounds that you might feel are loud thunder or the beats of a bass drum. In a sound wave, the particles of matter vibrate back and forth in the same direction that the sound energy is moving. The motion of each vibration pushes together some of the particles of matter. This part of the wave is called a compression. As the motion of the vibration moves away from the compression, the particles spread apart again. This part of the wave is called a rarefaction. The waves continue to form as long as the object vibrates. The way the sound waves move is similar to the way a spring toy moves. If you stretch out a spring toy, also known as a slinky, is what I knew as I was growing up, If you stretch out a spring toy and push one end, the coils of the spring move back and forth as the wave passes to the end of the spring. The particles of matter are not carried along with the sound wave. Each particle vibrates but remains in its place. Imagine what would happen if an air particle were carried with the sound waves. Sound waves from a choir's singing would cause a wind to blow. All right, next page now. Frequency and speed, and this is filling out mostly of that first page, 146. This is where you get all this information from. All right. Just looking at something here. Actually, we've already had some of it from the first page of the things that we were reading. All right, frequency and speed. Sound waves cannot be seen, but they can be measured. The distance from one compression to the next is called wavelength. Different sound waves have different wavelengths. These lengths are determined by how quickly the source of the sound vibrates. Sounds that vibrate quickly have short wavelengths. Machines and tools have been developed to help us see pictures of sound waves. An oscilloscope uses a type of microphone to convert mechanical sound waves into electrical impulses. The impulses are shown as a wavy line on a graph. The number of sound waves per second produced by a vibration can vary. As the number of waves changes, so does the frequency of the sound. Frequency is the number of waves that pass a point in 1 second. Frequency is measured in a unit called hertz. Sound waves travel in all directions away from the source of the sound. A sound wave can also travel through different types of matter. The siren of an ambulance can be heard whether you are in a house, in a tree, or underwater in a pool. Sound waves move at different speeds in different types of matter, though. The density, or how close the matter molecules are, affects how quickly the vibrations move from one particle to the next. The density of the matter also affects how far the sound waves can travel. Sound needs particles in order to move. Of the 3 states of matter, gas is the least dense, so sound moves the slowest through gases. The sound energy cannot easily move from particle to particle. Also, some of the energy gets used up as it travels through the spaces between the particles. This slows the movement of the waves. Air is the most common type of matter through which we hear sound. The speed of sound in air is about 335 meters or 1,100 feet per second. This is how fast sound travels through the air under specific atmospheric conditions. In different conditions, such as a hotter day, the speed of the sound will be different. The particles in liquids are denser than the particles in gases, so sound moves more quickly through liquids than it can through gases. The waves also travel farther than they can in a gas. Solids are the densest state of matter. Their particles are very close together. The sound waves easily move from one particle to the next. So sound waves can also travel faster and farther in a solid than in a liquid or a gas. The speed of sound is not the same as the frequency of sound vibrations. Sound speeds tells you how fast something is moving. Think of watching cars traveling on a straight highway. Suppose all the cars on this highway are traveling at 50 kilometers per hour. That's the speed of the car. However, the frequency of the cars is the number of cars that pass you in a set period of time. Frequency is how often they pass. In the first minute, perhaps only 1 car passes. In the next minute, 5 cars may pass. The speed of the cars stayed the same, but the frequency changed. The speed and frequency of sound waves are related in much the same way as the speed and frequency of the cars on a highway are related. All right, well, that's it for your science for today. Have a good weekend. We'll see you on Monday. Bye.